Reid, Wightman. So Digital Bond Labs is this new division of Digital Bond where we're focused on finding new vulnerabilities that vendors are not aware about and trying to fix those bugs before they become an issue. So we look for the kinds of vulnerabilities that I will show you today. I should say I'm a biased researcher, so I'm a strong advocate of performing red team testing on products. Obviously, I say that because it's one of the services that Digital Bond Labs offers. But honestly, I say hire any outside team from your development group to red team test your product. If you're a vendor, you can even build your own internal red team for your company. I think it's very helpful to have a non-developer test your product to look for security problems. So this is the outline of what we will discuss today. A quick definition of what vulnerabilities are, a look at what third-party libraries are typically included in industrial control systems equipment, and then we will look at some specific examples of vulnerabilities that we've found, and we'll look at 2 Japanese vendors who are affected by the issue in the third-party software. So my definition of a vulnerability is this. It's any mechanism which allows unauthorized changes to configuration or control. ICS CERT has a slightly different definition of vulnerability, although they seem to go back and forth on this. I think that the difference from ICS CERT and me is if a feature of a product lets you do control or configuration change without any security, then I call that a vulnerability. ICS CERT tends to call features which allow this access not a vulnerability. They look more at software defects as vulnerabilities. So I think that vulnerabilities include both real bugs, so software mistake in coding, as well as insecure by design, which is a phrase that you'll often hear Dale Peterson use when talking about control systems. So now that we have a definition of vulnerability, let's look at some third-party libraries. So a lot of embedded industrial equipment, and not just PLCs, has a lot of software that's not written by the vendor. A lot of embedded operating systems, so there's a very famous operating system called VxWorks that's in use by many control systems components. Linux is also used heavily, as well as Windows CE, or now I guess they call it Windows Embedded. There are also common embedded web servers that are in a lot of products, such as the Go-Ahead web server. And then there is also this library that we will be looking at today called CoDeSys. With third-party libraries, ownership is really the issue that we're discussing. Because as a vendor, when you use these third-party libraries, ultimately you are responsible for the issues in the third-party library. If your custom software depends upon the library, an end user can't patch the library or patch the software component without your say-so. And for an embedded system, if you're a vendor, you will have to provide a firmware update because customers can't generate that on their own. So as an example, Windows CE, the operating system, could have some bugs in it. For example, Windows CE was vulnerable to a known security issue in 2008. And so you, as the vendor, have to decide, well, first off, you have to keep track of Windows CE and know that the vulnerability came out. Then you have to patch it, and then you have to inform your customers that the patch is available. So let's look at the CoDeSys library. So CoDeSys is a library meant for use with programmable logic controllers. It consists of two main components, a runtime that runs on a PLC, which executes ladder logic, and it also has engineering software, which runs on a standard PC. So the CoDeSys software is used by hundreds of ICS vendors. I think the number was something like 250 different control companies use this software on their logic controllers. There used to be a list of the companies on 3S Software. So 3S Software is the company that makes CoDeSys. There used to be a list of the affected companies on their website, but they've since taken that list down. Right now, CoDeSys is mostly used in Europe, although there are some controllers targeted at the US and Japanese markets which are using the software. So the basic components, as I said, were the engineering workstation software used for programming the PLCs. The engineering software is nice for the engineers. The engineers can learn to use this software once, and then they can go and program any PLC that uses the CoDeSys software, since the interface stays the same. The software talks to the PLC with a small piece of code written by the vendor called the communication plugin. The other main component is this ladder logic runtime. This runs on the PLC, so it actually runs on top of an embedded operating system like VxWorks or Linux or the Nucleus real-time operating system and other OSs. The ladder logic runtime is responsible for executing the ladder logic, and it also contains network service. And the network service is meant for reading status from the PLC, as well as accepting commands from the rest of the control system. There are two other components to CoDeSys that not everyone uses. There is an OPC server, and there is also a communication gateway. And these, you don't need them to use the CoDeSys environment, but some people choose to install them. So the CoDeSys version 2 protocol was analyzed by Digital Bond in 2012, back when I worked for Digital Bond the first time. In 2014, just last month, we analyzed the version 3 of the CoDeSys system. The CoDeSys version 3 changed the protocol a bit, but they didn't change any of the functionality. So it has all the same vulnerabilities that the version 2 had. So version 2 let you upload ladder logic with no authentication. There was simply no password required. You could connect to the PLC and send logic to it. It also offered a command line interface, kind of a secret, but you could access the command line from the CoDeSys engineering software also. As an attacker, you could start and stop the process control or affect process integrity. You could also retrieve any file from the PLC, which some of these PLCs and RTUs which run the software are fairly complex computers that have full installations of Windows or Linux, and so the ability to retrieve any file on the system can actually help an attacker quite a bit. Due to the way that the ladder logic is written, you can upload a special ladder logic file which lets an attacker maintain access to the controller, and it could actually prevent the controller from ever being updated again. So this is actually a rootkit of sorts. In 2013, my colleague at IOActive, his name is Aaron Leverett, the two of us worked together and we scanned the internet for CoDeSys controllers. We found 680 controllers that were directly connected to the internet. We shared the information with incident responders in many countries. Some of those controllers are no longer accessible, thank goodness. but there are still quite a few that are available directly on the internet. So, CoDeSys version 3 has basically all the same problems as CoDeSys version 2. It probably will have the same directory traversal bug as CoDeSys version 2, meaning that we could access any file on the system, although the test PLC that we have didn't have any useful files on it to try this with. We're currently scanning the internet to see if we can find more CoDeSys version 3 controllers to see if there are any connected and to hopefully get them removed. So really the flaw with CoDeSys was that there was no security put on the communication protocol by the vendor, 3S Software. They may just have assumed that no one would figure out how their protocol worked. It's likely that they never had a red team come in to analyze their system to look for security issues with it. So my recommendations for companies like 3S Software and to their clients would be build a red team or hire a red team. I say if you're building a red team inside your company, it's best if they're dedicated to security work. They should learn how to use normal security tools and be focused on writing their own security tools. Many of these ICS protocols are proprietary or custom, so being able to develop tools to test those protocols is the most important thing. It's really important that a red team looks for design problems very early in the process, because once a product is released and out in the world, it becomes very difficult to patch a design problem. And we will talk about patching design problems as this talk goes on. Once development starts and the programmers start writing code, then it's important for the red team to start looking for programming flaws so that the flaws can be fixed before the device gets deployed. A red team really should have spotted the CoDeSys problems while the system was under development. It's pretty likely that none of the vendors that are affected by the CoDeSys problem have their own red team, or at least they did not apply it to their control system components. So the CoDeSys version 2 protocol is quite simple. The protocol starts with a sequence of 2 bytes. OXBBBB, that's hexadecimal. Or some of the data packets begin with this OXCCCC, also these hexadecimal bytes. The protocol then has a 4-byte length field, and then a function code, which is usually just a single byte, and then arguments to the function being called. The CoDeSys version 2 protocol usually uses TCP 1200 as its communication port, although some controllers use 2455, or of course some controllers use a custom port that the vendor specifies. We determined how the protocol works through just plain protocol analysis. As you can see, the protocol is quite simple, so figuring out what features of the protocol performed what actions was not too difficult. Also, later today, I will be posting a blog post with some of the tools used for doing this kind of analysis on the digitalbond.com website. So for CoDeSys version 2, 3S Software originally placed a password protection system on the engineering software. But the password protection was not actually enforced by the PLC. So the software would send the password to the PLC, and the PLC would send some data saying whether the password was correct or not. But as an attacker, you did not actually need to send the password to the software. If you just skipped that step of communication, you could still perform all of the actions. So 3S software provided a patch to the PLC, but to date, 0 vendors of the 250 vendors affected have produced a new firmware using that patch. And it has been, I think, a little over 2 years now since the vulnerability was public. So a friend of mine who has spent some time in this area tells me that he said that the PLC enforced password protection interfered with their OPC server. So when the OPC server connected to the PLC, it wanted to retrieve data, but the OPC server was not written to send a password to the PLC. As a result, the OPC server could get no data from the PLC. And he said that this is a reason most vendors have decided not to release updated firmware. The big lesson here is that patching an insecure by design system is too late in the process. So because other software, external software, is now dependent on this lack of security, fixing the security issue just becomes too problematic. Now you have to fix not only the PLC, you have to fix the OPC software. So really what you should do is apply a red team test to the components, as I said, early on. And then ultimately you have to decide whether you'll fix the problems that the red team finds, or if you'll live with those problems, or if maybe you'll stop using the third-party component entirely. I have heard from people that, that several companies contacted 3S software with concerns over this issue long before 2012, and that 3S software said, no, don't worry about it, we're not going to fix it. And so a vendor using their software that got that answer should have maybe considered using a different product. So there were 2 vendors who actually are not vulnerable that we know of, and they had an internal red team test their software, and they found the problem. And because they implemented their own fix for it, they saved themselves the trouble of having to release patched firmware. Of course, these products use their own developed authentication system, not 3S software's, so they're a little bit out of sync with the normal 3S protocol. So this is just to stress the idea that components that go into a system that have a poor design are really causing contamination to an industrial control system or any system. And it's simply, again, the fact that external components are going to expect the insecure behavior, and now those external components are going to be written poorly. So instead of fixing 1 bug, now you need to fix 2 bugs or maybe more. As industrial control systems get fairly complex fairly quickly, this bug might need to be patched in many, many, many places. So a great example of an insecure by design protocol that everyone here I'm sure is familiar with is the Modbus protocol. So Modbus, again, allows you to read and write data to a controller, and there's no security on the protocol. Because that's a legacy design, now everybody is vulnerable, and the only way to really fix it would be to change every device on the planet. So we saw the small explanation of the CoDeSys version 2 protocol. Let's look at the CoDeSys version 3 protocol. So CoDeSys version 2 only used TCP as its transport layer. CoDeSys version 3 can use TCP and UDP. Using UDP limits the attack surface somewhat, although there are some tricks we can use to get around the UDP limitations. TCP we have not thoroughly tested. The PLC that we purchased only supports the UDP version of CoDeSys. So we've only tested with the simulator and haven't explored it very far. So some notes as I explain the protocol. There's no documentation available to the public on the CoDeSys protocols. So everything I'm about to say is through, we figured out through reverse engineering and protocol analysis. 3S Software, I assume, shares some information on the protocol with vendors, with OEMs, but not with researchers. So the words that we use to describe the protocol might not match what 3S Software uses. So if you're a vendor and using this software, I hope I'm using the right words. The CoDeSys version 3, the UDP version by default uses port 1740, and the TCP version uses 11740. So the packet structure is a lot longer than CoDeSys version 2, especially when starting a session. The packets always start with this hexadecimal C5 byte. And then the packet also contains the last byte of the destination IP address and the last byte of the source IP address. The protocol then contains a checksum, a CRC checksum, and the first packet contains random data right here. So one of the interesting things about the protocol is that this checksum, this CRC, it took me a while to figure out how it works. And if we have time, I can talk about how strange it is. But this checksum is computed actually based on a function selector this byte is used to select. So the protocol is a bit strange because this byte chooses what CRC algorithm is used to apply to the protocol itself. So what we see here is the first packet from the master system to the PLC. This is a packet meant to say, hey, I want to log in and start communicating with you. The PLC then replies with a packet which contains a session identifier. And the session identifier are these green bytes here. The session ID is just 2 bytes in length. And you'll notice that this random data here, this is the same information that was sent in the initial packet. So this is to keep track of the session a little more accurately. And then once the session is established between the engineering system and the PLC, the packets get a bit of extra header data. They get an additional field, this red field, which is a master sequence number. And they also get this field that I've highlighted in purple, which is the slave sequence number. And they put the session identifier up here in these bytes. So effectively, what they're doing is they're using UDP, but they're adding sequence numbers that are similar to what you would use with TCP. So they're adding session ID and sequence numbers, which would be similar to the TCP concept of a TCP sequence number. And then I was just putting these slides together and noticed that this is actually a length field here. So this is little endian length, and then this is the CRC of the packet. And then the rest of the packet here is the number of bytes are calculated here. So that should be right, if I did my math right. So the protocol, again, had no security, just like version 2. So when ICS-CERT put out an advisory for version 2, they said that version 3 is not affected by these vulnerabilities. Well, ICS-CERT didn't say the right thing here. The protocol changed quite a bit. So the original tools used to test version 2 don't work with version 3. but version 3 has all the same problems as version 2. An anonymous friend tells me that ICS Cert probably just took this information from 3S software and repeated it. They didn't do any internal verification. He said that ICS Cert's policy is to just say what the vendor says in the vulnerability announcement. So I think that that's a pretty bad thing in this case, because many people might look at this and say, well, I'm running version 3, so I have no problem, when in fact they do. I should also point out that 3S software released some information in 2012 just saying that their version 2.3 runtime was vulnerable. So they get it wrong too when they release their vulnerability announcement. It's also worth noting in their announcement, they say the patch is only available to their OEM customers. So the patch is not available to end users of the component. And this, again, is like I say, the vendor has to apply this patch to their firmware and then turn around and give the firmware to the end user. So the big lessons to learn here are a lot of third-party library vendors are going to say, like, we don't have a problem. If you're a vendor that's integrating a component into your product, you really should ask to see their security development lifecycle documentation. Ask them, what are you doing to test the design of this component, and what are you doing to review the code of the component to make sure that there aren't bugs in it. And then finally, trust but verify. Even if the vendor is doing or appears to be doing a good job, it doesn't hurt to look at the product yourself as you integrate it into your final device that you're going to sell to the world. So let's look at some affected Japanese vendors of the CoDeSys vulnerability. The first one is the Hitachi EHV Plus line of PLCs. This device is mostly sold in Europe. It runs CoDeSys version 3. It was actually a bit difficult to get in the United States. To purchase this in the United States, I had to buy it from a European reseller. So the EHV Plus runs CoDeSys version 3. We tested the EHV CPU 1025. The device only speaks the UDP version of the CoDeSys protocol. It actually had the secret command line that I mentioned earlier. It had that feature disabled in the product. It's possible that we could enable TCP, and it's possible that we could enable the command line. I'm not sure if it will work, but there is a configuration file on the PLC that lets you enable additional parts of CoDeSys, and this might be used to include TCP service and include that command line. So far, we have not been able to do it, though. Before we talk about Hitachi too much, I want to say they actually did a lot right with this controller. So the EHV Plus has only one service turned on by default that we can tell, and it is the CoDeSys protocol. So it didn't have any open TCP ports, which is nice. A lot of vendors tend to throw, I think, too many features into their products, where they put a web server on their device, or they put some debugging features. There didn't seem to be anything like that on the EHV Plus. So in one sense, the Hitachi EHV Plus has a smaller attack surface than most control system components, and that's a good thing. But on the downside, we didn't see any mechanism for applying a patch to the controller. So because that only open service was the CoDeSys service, and CoDeSys is meant for ladder logic, not for uploading a firmware, it doesn't seem like it's possible to update the firmware. But maybe there is some internal way that we haven't discovered. We didn't pull the firmware off of the controller yet to reverse engineer it and see if any of those features are there. I should say this controller uses Renesas, which is formerly Hitachi CPU inside. And the CPU is one I haven't actually worked with before. So extracting firmware from the CPU using JTAG isn't something that I've done before. But we probably will. So to exploit UDP on the CoDeSys controller, like I said, there is no security on the version 3 protocol. So there is just that session ID that's used for controlling access to the PLC. So that session ID was 2 bytes long. That means it can have a value of 0 to 65535, which is 65,536 possible values. The Hitachi PLC increments that session ID by 4 each time you try to connect to the device. So really, there are only 16,000 possible session IDs with this controller. We didn't see any mechanism for adding a password with EHV labeled version of CoDeSys, so it doesn't seem that that feature will work. And I don't think it, well, if it has the same issue as version 2, it wouldn't do anything either anyway. So we wrote an exploit script to test some of the malicious features that an attacker might do against this controller. So we can stop and start process control with it, start and stop the CPU. We can retrieve and send new ladder logic to this PLC. We can upload a new configuration file to the controller. And we can also do some other administrative functions, like we can change the controller's IP address. So to attack UDP is kind of interesting. The IP stack is a little bit broken for CoDeSys version 3. When you send a UDP packet to CoDeSys version 3, you can't always get a response. And the case that you can't get a response is when you're attacking from a different network. So I may scroll back a little bit here. I apologize. This packet, if you remember, has these 2 fields. It has a destination address and a source address. But these addresses are only the last byte of the IP address. So the problem is, if you're attacking the controller from a different network, what value do you say for your source address, especially if your source address is on a different network? So the problem is that if you attack the controller from a different network, you send a session request to the PLC as an attacker through a router. The PLC will receive that packet and will generate a reply, but it has to decide who to send that reply to. Well, it turns out it will send it to a computer on the local network with the PLC. And that computer might not even be on the network. It might be an empty IP address, or it could be a computer that's not related to CoDeSys at all. So the PLC will send this reply to the computer because it doesn't know how to route the packet out of the local network. But that's okay, though, because as an attacker, all we have to do is guess the correct session ID, and we can continue issuing commands to the PLC. And so there are only 16,000 possible session IDs. We can either assume the session ID is 0, because it will always wrap around to 0 eventually, and just continue to try the same sequence of commands over and over again. That case will take about 4 hours maximum to compromise the PLC or to stop it. And if we want to be faster but a little bit more noisy, we could just try all 16,000 session IDs all at once. And that process would take only a few seconds. You're limited just by the network speed. And these packets aren't very big, so it wouldn't take long. So that's a look at Hitachi, who was vulnerable to CoDeSys version 3. So let's look at another vendor that had some of the same issues. Sanyo-Denki produces a robot arm controller called the SanMotion C. this controller runs CoDeSys version 2, the older version of CoDeSys. It also runs VxWorks as its operating system, and it has the VxWorks debug service enabled. So it actually inherits several vulnerabilities from several components that it contains. In addition, it contains some backdoor accounts, and it has some debugging services for CAN protocol open on it. So when I was first looking for Japanese vendors that ran CoDeSys, I found this Sanyo-Denki SanMotion C controller. And I got kind of excited because I looked at this hardware, and then I turned and looked in my lab. And I already have in my lab. So if we look at these two controllers, they're identical. They have the same hardware, they just have a different label. And so I started to dig a little deeper, and I found another controller that looks identical called the CoDeSys CP232Z, made by the Austrian company Keba. So these controllers are all the same hardware, it turns out, or at least they appear to be, and it turns out they are. So the firmware on all of these controllers is identical. The firmware is also used by a bunch of other companies here. These are all the names of the companies affected. I probably don't know how to pronounce some of these, but they're primarily companies in Europe, and they all do pretty much the same thing. These companies make robot arm controllers for manufacturing. So we're trying to figure out who actually makes this hardware, who actually makes this system. We think the original manufacturer of the hardware is probably Keba. The firmware contains a lot of functions inside of it that have names. And some of the functions have names of companies, I expect, because they have some special function that only that company uses. Keba has thousands of these functions with, Keba print data, that sort of thing. And the other companies have very few of these special functions. So it led me to believe that Keba probably are the original designers of the system. So there are a lot of other components that go into this system. VxWorks, I mentioned, CoDeSys, which we're talking about, and there's also the CAN open protocol stack and some other third-party components that we can figure out from reverse engineering the firmware. And all of these have potential vulnerabilities. So the issues with the Sanyo-Denki PLC are the CoDeSys version 2 problems. So all of the version 2 problems exist on this system. We can do all of the attacks that I showed earlier as issues. We first contacted Festo about the problem in 2013 through ICS CERT. And after a year of going back and forth with Festo, ICS CERT got fed up and they just released an advisory because Festo was refusing to fix the problem. So there is this ICS CERT advisory, this ICSA 1408401. This advisory you can go and read, and it shows, ICS CERT contacting Festo and Festo refusing to fix the issue. These controllers, the Sanyo and the Festo, also have a much older issue called the VxWorks debugging service. So this issue was first made public in 2005. It's worth noting that these PLCs were released as products in 2010, 5 years after the VxWorks vulnerability was publicly known. So the vulnerability was known for 5 years before the product came out, and the product still had the issue. And then there were some other problems in these systems. There is a backdoor FTP account that can be used, not that you need it, because the CoDeSys protocol lets you send and receive any file you want, but you could use FTP to do it too. And it also has this CAN bus debugging protocol port. which I haven't played with much because there's not really a need to exploit that. So there were 9 total companies using the same exact hardware and firmware in this case, and none of them spotted the security problems with the system that they were selling. So I think it's pretty likely that none of these companies are doing any security testing inside. The question that I have for the companies that I would love to find out from them is whether they share hardware information with each other. For example, if resistor or other component inside of their PLC was failing, would they let each other know about that issue? It becomes relevant because, are they sharing security information with each other either? We probably will never find out. So the conclusions of this talk should be, it's most important to identify security issues before you release your product. If you're a vendor, you should start by building a list of all of the software that you don't write, all of the third-party software, and monitor that software for vulnerabilities. This is still kind of a new area for a lot of vendors that they haven't quite figured out yet. So in the Sanyo-Denki example, their controller was released in April of 2010. That's the earliest document I could find with a sales brochure. I think it actually had a release announcement. So that was 5 years after the VxWorks issue that was still in the device. In the Hitachi example, yes, the EHV Plus line was released before the CoDeSys vulnerability was known about. I think the EHV Plus line was released around June of 2010. But this really should have been noticed during internal testing. It should have been some developer or security tester looking at this protocol and saying, why are we not doing any authentication? Final conclusions are, as a vendor, you really need to plan to patch your system. These security issues are going to come up. Just 2 or 3 weeks ago, there was this famous bash bug or shell shock or whatever you want to call it, vulnerability that affects a lot of embedded products in the ICS space. There are still a lot of ICS components that have no ability to update the firmware at all. So planning to patch and understanding that you need a secure firmware update mechanism, and you also need a mechanism to discuss security issues with your clients is something that vendors need to start improving quite a bit on. So if you secure your product by design first, that is, at least require basic security like authentication, the other bugs that you'll find in your patching strategy should be easy to fix because they should just be programming bugs that don't affect interfaces to the system. Some famous kind of examples of patches that don't really do anything that have come up recently are the Schneider patch. So Schneider had some vulnerabilities found in its web server. Schneider released firmware updates to fix the programming flaws in its web server, but its Modbus server still has insecure by design problems. The Modbus server on Schneider has basically the same problems as CoDeSys. It allows an attacker to upload new ladder logic or to start and stop process control, things that Modbus normally does not allow you to do. And another example is 3S Software actually has a component on their PC software had an issue where there was a directory traversal bug in that software. It was found by a researcher named Aaron Portnoy. It took only a few months for 3S Software to patch that bug, but years later we're still stuck with their insecure by design issues simply because patching insecure by design is essentially impossible. So with that, if anyone has questions, I would be happy to answer.
Okay, we'll open it up for questions. One thing you might want to clarify, because it's so important, is what is the impact? Okay. Could you clarify what is the impact of being able to upload ladder logic?
Well, I mean, you're effectively, you could say it's like a Stuxnet vulnerability in some sense, because you're able to upload new process control logic and change how the PLC is dealing with the inputs of your process control system.
Okay. Questions? No brave souls out there? Well, let's talk then a little bit about kind of the chain that we have here. So you've got the third-party library.
Right.
And then you've got the vendor that is using the third-party library.
Right.
And I think you've talked a lot about how they have to test that code and that sort of thing. But then let's go down the chain a little bit. So then you have ICS cert and the certs that, you know, and like JP cert relying on ICS cert and all the certs kind of sharing this information. They essentially said version 3 was not vulnerable, probably because the vendor said it was not vulnerable. What do you think a cert should do?
I think a cert should really just discuss the vulnerable version that the vendor is willing to admit is vulnerable. If a vendor says that, you know, some future version of their software is not vulnerable, I think it really should be up to the vendor to prove that to their customers. It shouldn't be the cert being the mouth and saying that, you know, this device is, or this system is not vulnerable. I think ICS cert kind of markets itself as being necessary as ICS cert because they have some special inside knowledge of industrial control systems. But if all they're going to do is replay what the vendor tells them and not actually apply their ICS knowledge to a controller, then you know, what even is the point of ICS cert?
And I guess there's probably all different levels of checking that they could do, from actually installing and testing it to even basic interview.
Right.
Did you add security to the protocol? How did you fix this problem?
Right. And I think that as a security researcher, you know, I knew that CoDeSys version 3 was vulnerable from playing with the controller for about 5 minutes. Because all I had to do was get the engineering software and set up the PLC, and then I can see that the software has no mechanism to ask for authentication. The lengthy part is figuring out how the protocol works so that I can write my own tool to use the protocol. And that's really just the proof of concept.
Hi, Reid. It's Corey. Real quick, so with ICS Cert facilitating your initial discussion of the vulnerabilities with CoDeSys, did they facilitate on the way back for when they said version 3 is not vulnerable?
No.
There was
Right.
no contacting the
No.
researcher in the first place to help verify it? Okay.
Right.
That was my question.
Right. And I didn't have any way at the time of verifying whether version 3 was vulnerable or not anyway.
Other questions? Okay, well, let's step down the next thing. So now we went CoDeSys, vendor, cert, customer, end user.
Right.
What is an end user supposed to do related to these, you know, these third party? Because I guess the other thing is, you may never know that your system has this third party library in it.
Right.
You could be following your vendor's bulletins and all that and just never know that this component in the vendor caused your system to be vulnerable. So what do you do as a customer?
Well, I mean, in the specific example of CoDeSys, it's pretty obvious to an end user that they're running CoDeSys because most of the software, it gets like a label put on it from the vendor. For example, Hitachi puts the Hitachi logo, but it still says CoDeSys by Hitachi, you know, as the logo for the software. But in the general case, that's not always true. And it's a very difficult problem for an end user to solve. I think that if an end user is very proactive, they could ask the control component maker to provide a list of all of the third-party software used and put that under contract. Say, you know, we're going to buy your device and you have to share this information with us. And if you're incorrect, then that's a breach of contract. Could be one way to go about the problem.
And I just wanted to point out that this, and you can talk to this a little bit, this is not unique to CoDeSys in the sense of oftentimes vulnerabilities will be found.
Right.
And tools will be developed to scan and exploit those vulnerabilities. And the fix, the quote fix that a lot of vendors will put in place is to modify their system just enough so those tools don't work, but not to fix the underlying vulnerability.
Right.
And we've probably run into that more than once.
Mm-hmm.
Yeah, so, and I don't know how as an owner-operator you solve that, but ideally your vendors, you know, this is again, as I was talking about this morning, these problems are going to happen to every vendor, and it's really how they respond to these problems. You know, do they actually fix the problem? Do they actually, in the case of a third-party library, are they proactive, talking to all the people that have integrated their products and providing them with a path to get to a secure product? You know, if they do those sorts of things, and then you have some faith that the next time there's a problem, they're going to do the right thing as well.